Good morning, everyone, and welcome to the Power Grid International webinar, Aerial Covered Conductor Systems as a Wildfire Mitigation Tool, brought to you by Hendrix. I'm Power Grid International Editor-in-Chief John Engel, and before I turn it over to our presenter, I want to remind you that we will be taking questions following the presentation, and you could submit those at any time in the chat box on your screen. All right, so let me set the stage for this webinar. Recent years have shown an increase in wildfires in the western regions of North America. The wildfire-prone regions are growing, as is the damage caused by those fires. While an objective of system designers is to harden the electrical grid infrastructure to survive wildfires, a more pressing concern is to design and build power lines which do not cause ignition in the first place. This webinar will describe how wildfires are initiated and the challenges power lines face in wildfire-prone areas. We'll discuss fire-related characteristics of bare wire and underground systems, fire mitigation techniques offered by both spacer cable and tree wire systems, and the effectiveness of various fire mitigation strategies as evidenced through lab and field testing. Please also check out the documents in the handout section of this platform to follow along and get additional information. I'll pop back on for the Q&A, but for now, I'm excited to turn it over to Brian Traeger, Director of Technology and International for Hendrix. Brian, you can take it away.
Great. Thank you for that much appreciated introduction, John. So, hello, good morning, webinar participants. Thank you for taking the time out of your busy schedule to join us here today. For me personally, it's always a privilege and a pleasure to share new ideas and new technology with my industry. So without further ado, we'll just try to go ahead and get started with the presentation material. Again, as John said, we're going to talk about aerial covered conductor as a wildfire mitigation tool. In the presentation, we'll talk a little bit about wildfires and power lines, and then talk about how different construction types respond, whether it's bare wire lines, bare wires with insulators, going to undergrounding, and then the different types of covered conductors that we have, whether it's tree wire or spacer cable. And then we'll talk a little bit about the testing so we can make sure that this is all real. We'll talk about objectives and motivation, and then we'll see if we can try to make some summary and conclusions out of the whole thing. This should not be a seminar about how wildfires are caused, but I just wanted to get us all on the same page about some of the ignition mechanisms. So obviously we have one of the big things is lines blowing into trees during high wind events. They could have enough current to cause ignition, or they could cause a spark. We're talking about downed lines when lines actually come off of the pole and lay on the ground. We know that 30% of the cases where the conductors hit the ground are what we call high impedance fault. We don't have enough current to trip a fuse or a breaker or what have you. And those lines for a high impedance fault will lay on the ground until it may be too late, until we have a fire. And then sometimes they will call and it will be too late. Then we have vegetation contact. We may have a tree branch above contacting two lines that might be there for an hour, 24 hours, who knows, on there long enough to draw enough current, maybe burn the line down or have a branch in flames fall to the ground and ignite dry brush on the ground. A couple of mechanisms there that could turn into a fault, turn into a wildfire. We have conductor clashing. The conductors may be flopping back and forth in high winds. If they're bare wire, slap into each other. This is going to cause really super high temperature plasma to fall onto the ground and certainly ignite anything there. And then we have what we call repetitive faults. We keep getting the same fault on the same feeder. If each fault creates some risk of failure, we may have aged equipment. That's going to add to the possibility, blown bushings, what have you. So we got to be cognizant of those ignition sources. And then we have apparatus failures, whether that's bushing, cap banks, clamps, line switches. And over time, they can increase in intensity and ignite what we call proximate combustibles. So we want to hopefully avoid that as much as possible. Here's perhaps the most insidious and perhaps the most preventable, what we call mylar balloons. So we've got statistics from Southern California, Edison, PG&E, up to, up 1,000 or more faults caused by mylar balloons. And when they go, I mean, the explosion is unbelievable. And they can blow all kinds of hot stuff on the ground and start a wildfire. And they have started wildfires in numerous cases, both in California, Arizona, and surrounding areas. California introduced legislation just recently to adopt the standard for a new Mylar balloon. Those not compliant with that standard, those balloons will be outlawed in 2031. But no doubt we're going to have a good additional 8 years of wildfires from Mylar balloons. If we were smarter as a society, we wouldn't be promulgating. Here's a big question. We were working with wildfire mitigation since the 90s, basically, with the Australians. And the big question there, when we talked to the Public Utility Commission in Victoria, basically, do you want your equipment to survive a wildfire, or do you simply want it to avoid being the cause of a wildfire? If we want to survive it, it's not always possible. Certainly it's not easy, and it's certainly not cheap, surviving wildfire. How you harden systems do monitoring, certain relaying, REFCL, neutral equalizers, fiberglass cross arms, steel poles, simulation, monitoring. I mean, yeah, these are things that really need to be done as part of survival. But we are talking here about avoiding causing a wildfire, and that is the fundamental objective of this webinar. And we're saying that there options exist to mitigate against the possibility of a power line starting a fire. And that's what we're looking at. So our objective is to eliminate the possibility of a wildfire being caused by an electric utility power line. And we'll talk about what tools and or techniques can we employ for various power line construction options, whether that's aerial, whether it's underground, whether the aerial is bare, whether it's covered, and to provide a maximum assurance that they will not ignite or contribute to a wildfire scenario. So let's talk first about bare wire lines. We know that bare wire lines are intrinsically vulnerable as a source of ignition for wildfires. That line may fall to the ground energized. Staying on the ground long enough, it's a high impedance fault, but it will give you enough current to ignite a wildfire. We have the possibility of that bare wire coming in contact with a tree. Tree may be dry. It may have dry material on it. It may have a low impedance. That will cause ignition. That line may fall to the ground de-energized. The bare wire line de-energized falls to the ground, can hit a rock, throw a spark onto dry brush, and ignite that. And then we already talked about conductor clashing. Two conductors slap into each other, causes a massive fireball, throw molten metal downward, and ignite it. So how can we try to eliminate these wildfire ignition scenarios from bare wires? Well, the first one we're going to try to do is avoid what we call conductor clashing, when the conductors slap into each other during high winds. So what we want to do is maintain separation of those bare wires at mid-span. If we maintain the separation at mid-span, they won't be able to slap into each other. We have various manufacturers make these interphase spacers. It's basically a nice fiberglass rod. I'm showing you there with the other Hendrix insulators on either side. There are other options. There are other manufacturers that don't use insulators. They use clamps. They put the insulators on the fiber rod, which is fine. This one here, it accepts all conductor sizes. Other suppliers exist. There are heavier models. There are lighter models. They're pretty darn easy to install. The one shown here as break-off torque bolts for easy installation, fiberglass rod with high-density polyethylene, insulators for end fittings, and the lengths can go from 36 inches to 120 inches, depending upon whether you're 15 kV or 25 kV or 69 or 115 or what have you. There are various manufacturers and various suppliers of these. They all look pretty darn good, and it's a viable method to avoid conductor clashing. The next thing we want to talk about is what kind of insulators we're using. We have been introducing what's called flame retardant insulators in the last 5 or 10 years. So we know that a polymer insulator will ignite if the exposure temperature exceeds its ignition temperature. So these are kind of interesting things. We know that wildfire temps are easily 1,100 degrees Fahrenheit up to 2,000 degrees Fahrenheit and even hotter than that. And we know that HDPE ignition temp is around 650. So if we get a static wildfire, that thing's going to go on fire, right? 650 versus 2,000 degrees. Yeah, it's going to be ignited. So we don't want insulators or anything on the system to be fuel for a wildfire. So if we use flame retardant insulators and we have a passing wildfire that's passing kind of slowly, maybe, that insulator will ignite if and when it's exposed to an open flame for some number of seconds or minutes. We know that that insulator, because it's FR insulated material, it will self-extinguish after the heat or flame is removed. So even if a power line is impacted by a wildfire and extreme heat flames, it will not propagate fire to any other element or area. And this is critical. We don't want to be the cause of ignition. So we're going to do everything we can to avoid that scenario. Yeah. So when we look at FR insulators, we know that cross arms and poles are flammable. Possibly brush is on that cross arm. Even if we're using a non-combustible cross arm and a steel pole, I still may have brush or foliage on that cross arm. If that insulator, for any reason, becomes ignited, we don't want flaming drips to fall on any ignitable material, either on the cross arm or on the ground. So no dripping removes concern for bringing a fire at the top of the pole, which will extinguish as soon as the wildfire passes, to ignite something on the cross arm or beneath the pole. Okay, so this is one more system hardening technique to ensure that anything that's on the top of the pole doesn't go to the ground and ignite either the pole or the ground. So that's one more belt and suspenders technique we've got here. What are the flammability standards for insulators? Well, we find out that there's no flammability standards do exist for insulators, whether we took an NCC 29 or what have you. So we have to, as suppliers, look to UL 94, which is the standard for safety of flammability of plastic materials for parts and devices and appliance testing. We also have ASTM D3801 and IEC 60695, but these three standards are essentially equivalent. So what we have done is we've gone to UL 94 and evaluates flammability behavior under an open flame, which makes sense. We want to see how fire retardant they are, really. The VO, or vertical burning requirement, is the most stringent. What we do is you test and you put cotton balls located about a third of a meter, a foot and a couple of inches below that burning sample. And they should not ignite by flaming particles or drops. So, of course, the only way to get this test done is send it to a independent testing laboratory, and we passed UL 94 with flying colors. What most of you folks know about testing is that we always test on on what we call plaques, and plaques are like a deck of cards. You put it in a test chamber, you test it, and then you make all kinds of conclusions, and we were able to test one material versus another. Our engineers said, well, we need a test that's a little more representative of what's happening in the field. So even though there is no standard written for one, we wrote our own standard. So again, raw material type test intended to compare different materials. We did an in-house test designed to test real life condition using insulators rather than plaques made from raw material. So not only did we not use raw material, we used finished material. Insulator subjected to a utility torch flame directly applied to the fin. That fin is 1/8 of an inch for 30 seconds. That flame, when that flame was taken away, that flame self-extinguished in less than 5 seconds. And the melted drops from insulator self-extinguished before they hit the ground and did not ignite the cotton balls 2 feet below. Very happy with that test. And we know that our affiliate in Australia also did that test to the requirements of their Public Utility Commission there. So how about undergrounding of power lines as a wildfire mitigation tool for power lines? At first glance, underground cable seems to be an excellent solution. Underground is out of sight. Underground can't throw a spark onto dry brush. It's not subject to vegetation contact. We love underground. It seems to be the best thing since sliced bread. But with our underground cable, there are a couple of drawbacks to using it for wildfire mitigation. First of all, the cost of materials for underground is 3 to 4 times the cost of covered conductor. and 5 to 10 times the cost of bare wire. And if you start looking in urban applications where you got to dig up the pavement and move materials and move other lines and all kinds of stuff, it's not 3 to 4 times covered conductor or 5 to 10 times bare wire. It could be 10, 20, 30, 40 times the cost of an aerial system. With underground cable, we have to look at the cost of underground transformers. They're a little bit elevated. We have to look at the potential harm to tree roots and other environmental concerns. It's kind of hard to trench a hole without digging up roots, right? We have to look at the lack of flexibility for underground cable. How long will the medium voltage network remain unchanged? What is the future loading going to be? Are we going to reconductor? And how will those changes be handled? So we have to look at underground as some capital to install underground for future, whereas we install aerial conductor for now, and we can easily add, change, or modify in the future. So the trend pretty true of all aerial networks. So some are using underground cable for power line related wildfire mitigation. Undergrounding is technically viable and extremely attractive option for wildfire mitigation strategy for power lines, but it's also very expensive. And the lowest cost of avoiding wildfires, improving reliability, and still allowing for flexibility in network modifications without skyrocketing future costs points to the use of aerial covered conductor. When Southern California Edison, they studied the effectiveness of alternatives. They really put a lot of effort into this, bare wire versus covered conductor versus undergrounding. And they published a couple of IEEE papers and magazine articles. Are absolutely brilliant describing their work, and I recommend you look that up on Google it and print that stuff out. They really did a great job. But they took a look at the relative mitigation effectiveness factor. So they said, well, if I use bare conductor, that's only 15% effective. Not sure where they got that number. If they reconductor using covered conductor, they said it would be 60% effective. I don't get how you get 60% effective. I would think it's much higher than that. And I saw a paper from Southern California Edison published right after these numbers came out that they said it wasn't 60%, it was 70% effective. That's okay. Let's go with these numbers. Underground conversion as a mitigation effectiveness factor, they said that was 1.0, which we love underground cable. I mean, it's the best thing since sliced bread, but it's certainly not 100% effective because other things happen, bushing failures, whatever. Anyway, let's go with these numbers. They did the cost per mile. So bare wire, they said, 0.3 million per mile, covered 0.43 per mile, and underground 3 million per mile. And then they did a mitigation to cost ratio, which they said was the effectiveness. Bare wire was 0.5, covered conductor was 1.4, and underground was only 0.33. So the conclusions they did from studying those wildfire mitigation strategy alternatives was that covered conductor was easily the most viable, cost-effective mitigation tool. And underground conversion, although it was massively a significant mitigation strategy tool, it had a very low effectiveness mitigation to cost ratio. So let's talk a little bit about what our covered conductor configurations are. We have two. One on the left, one on the right. The one on the left is spacer cable. We've got, or rather on the top, 3 heavily covered conductors supported by a messenger and separated and hung by spacers. Okay, it's got a very narrow right of way. You can see it's about 12 inches side to side. California, we're using 18 inches side to side, but it's 12, 13, 18 inches side to side and top to bottom. If we go with tree wire, it's the same heavily covered conductors, but strung in an open wire configuration on cross arms with poly insulators. And again, you can use more shorter or more narrow cross arms to get a more narrow right of way, because if we have conductor clashing, there will be no current. We won't have a fault or an outage. So we did a lot studying the difference between tree wire and spacer cable as a mitigation tool, and which is better and why. We said, well, basically there's no difference between spacer cable and tree wire with respect to wildfire mitigation, unless on the left, a fallen tree comes and sits across all 3 phase conductors, abrades that covering, creates a bare wire, and then we start throwing sparks and having a problem. Yeah, so that's the difference. But the differences that arise are those related to foliage removal and tree trimming. Spacer cable uses much less right of way than tree wire. and you're saving literally 80% of your tree trimming, literally 80% of your foliage. What are we to do with selecting one of these two options for wildfire mitigation for aerial covered conductor? So what we decided was going to use tree wire when there's no trees, which sounds absolutely absurd, but the concern out west is that we can have a palm frond that becomes ignited, whether the existing wildfire or power line or whatever, and this palm frond can fly literally a half mile to a mile while still being ignited, drop somewhere else and create a wildfire there. So now the utility is, responsible for that wildfire in a new location. It can also fly between bare wires. That's a different issue. So we're going to use tree wire where there are no trees. We're going to use spacer cable when we have treed areas, when we want reduced right of way, when we're putting 2, 3, 4 circuits on those poles, et cetera, et cetera. So that's the difference in strategy. We wanted to talk a little bit about the flammability issues for covered conductor. The current state of the industry, where are we? The cable becoming overheated and igniting itself. What's the possibility of a passing wildfire igniting the cable? And what is the possibility of a covered conductor jacket igniting and carrying the flame to another area? Well, the current state of the industry is that, number one, flame retardant has not been used to date for medium voltage covered conductor. We saw an article in one of the magazines, Bear Valley Electric in California, published an article saying they were using FR cable covered conductor and getting some good results out of that. I have no idea. They did not publish any type test. They did not publish what standard they tested to, and it turns out it would perhaps in the material they're using is not even flame retardant. It's what's called flame resistant. We don't know where that cable is coming from. But anyway, that's a data point. Number two, what is the perceived need application for FR additives? Well, we're going to enjoy the higher ignition temp. Not going to be much higher, but it's going to be higher. We're certainly going to enjoy the anti-drip properties so that the cable extinguishes when the flame is removed. Problem is that, and I alluded to this previously, the temperatures at which the wildfires exist exceed the ignition temps of polyethylenes, regardless of their plain high-density polyethylene, whether it's cross-linked high density or whether it's cross-linked high density with a flame retardant version. They will all ignite. So the FR properties assumed of minimal benefit in light of the fact that any static wildfire would still result in ignition of the cable. But the issue is still under intense discussion, as well it should be. And we do know that FR cable will be more resilient and less prone to ignition in the event of a passing wildfire. So this is something we're looking into, something we should look into, something that's going to increase the cost of construction of materials, but we should be looking down that road. So these are some of the issues we discussed with the California Public Utility Commission years ago. What's the possibility of a cable becoming overheated, igniting itself, dropping to the ground, and creating a wildfire? Good question. Well, we have protective devices on those lines, reclosers, breakers, fuses, and we have not only protective devices, we have backup protective devices that remove the circuit in case of an overcurrent or a fault. We know that ICEAS 121.733 standard for tree wire and message-supported spacer cable requires cross-link to have a higher temp rating for covered conductor. So these, again, are higher temp ratings. Is that going to make a difference? Marginally, probably not. And lastly, we've never had a recorded incident of a protective device or a backup device protection failing to operate and igniting a covered conductor. So what's the possibility of a cable becoming overheating and igniting itself? About as close to zero as you can possibly get. What's the possibility of a passing wildfire igniting the cable? Another good one. Well, wildfires usually pass by pretty darn quickly, especially since they're quite often wind-related events, leaving the covered conductor, a cable, unharmed. If that wildfire is static, if it's motionless, if there are no winds, it's just sitting underneath the power line and cooking away at 2,000 degrees Fahrenheit, well, probably everything is going to be burned, not just the cable, but all the surroundings. And again, as we said before, any and all cables might burn, whether it's HDPE, XLPE, or flame retardant mixtures. Lastly, we have no recorded incidents to date of a wildfire igniting a covered conductor. Here is a case. This happened around 95. You could look it up. This is in the Great Smoky Mountains National Park. We had a 15 kV line to an antenna farm, an antenna site up on the top of the mountain. The U.S. Forest Service set a controlled burn. That controlled burn unfortunately got out of control, started a wildfire. I think it went for 3 days. That wildfire was extinguished with rain. I was the engineer that did this inspection. We had a little bit of charring on the poles. It went up in a bucket. There was no damage to the cables. There was no damage to the hardware. We cleaned it up, re-energized it, and that was one data point that we did not have a wildfire igniting our covered conductors. One data point. Here's another one. This happened in 92. It was called the Great Gatlinburg Fire. Entire city block burned directly below a double circuit spatial cable. Here's the photo. You can see a good part of the city was burned to the ground. These lines, for some reason, right next to the burning were not damaged. And the only conclusion I can tell you, great, we didn't suffer any damage from a passing wildfire. The reality is probably that the wind was blowing into the screen here. So if it was blowing the other way, we probably would have had some damage. Did an inspection, everything was fine. So another data point, we survived. How about, can a covered conductor jacket ignite and carry the flame to another area? This is what I call the Mission Impossible scenario. You light a fuse and it's going off and it's going to create a wildfire in another area. Don't see how this could happen if a flame was high enough and remains long enough, 2,000 degrees at 40-foot elevation. It's probably a good bet that everything on the ground is already ignited, not only already ignited, but already charcoal. So there's no recorded evidence that this has ever happened in 72 years of experience and 500,000 miles of covered conductor installed, but still worth asking the question. So flammability issues for covered conductor. FR cable is not yet used. Jury's still out. I imagine it's coming. Benefits are still under consideration. Cable becoming overheated and igniting itself, not likely, and we've never had a recorded incident. Passing wildfire, igniting the cable, certainly possible, but inevitable in a static fire, regardless of what the cable is used. Once we have 1900 degrees at 40-foot height, we've got burnt stuff on the ground. Covered conductor jacket igniting and carrying a flame to another area, not likely, never happened. Don't see it happening. We wanted to talk a little bit about what our colleagues at Southern California Edison did, and again, they did an unbelievable amount of testing, and all of this testing is available open source on the IEEE. They did an absolutely brilliant job. I'm showing the lab testing. They had outdoor testing that was also published. So what they did is they wanted to see, what's going to happen. So they tied all 3 phases to a wetted tree branch, and you can see that tree branch on the side there. And they shorted the 3-phase conductors to each other and to the tree branch, and they tied them on there pretty darn tight with plastic ties. It was 15 kV cable. They energized it at 3x, 35 kV. They ran that test for 8 hours, which they said was typical of a trouble crew's response time in mountainous areas. Stopped the test, no burning or damage at all, no damage of any marks on the surface. We did a similar test at Hendricks. It lasted 1 year without a short circuit. Same, but we didn't test it for 8 hours. We tested it for a year. Those results are also available in the IEEE. If you can't find it, send me an email. I'll send you those papers. SCE, Southern California, said it demonstrates that covered conductor will not cause ignition for tree or ground contact, even for an extended period of contact. Then they went on to test on the infamous Mylar balloons, and they did 2 test setups. One balloon was phase the ground, and the other test was with the balloon between the phase. So phase the ground and phase the phase. They ran these tests for 2 hours each. They did all kinds of monitoring, PD, thermography, and some other complicated stuff. After 2 hours, they disconnected it, and there was no flashover, no current or evidence of burning or tracking. And they said it demonstrates that Mylar balloons will not fault when trapped on the covered conductor lines. And when we were doing this testing for 2 hours, we didn't really know what to expect. I knew what to expect, but nobody else knew what to expect. I mean, this is pretty hairy. You got a real hardcore short circuit between the phase and ground with a metal object. And one of the technicians said, after an hour and a half, hour 40, he said, relax. This was bare wire. It would have exploded violently within 60, 90 seconds. If we're here an hour and a half, we still don't have any current, we still don't have any heat, this thing isn't going to blow. So similar configuration with Mylar balloons and bare wire lines will result not only in a flashover, but a massive flashover and a fireball with it. So solve your Mylar balloon problems. So how effective is covered conductor in preventing wildfire ignition? Covered conductor has been used for wildfire mitigation since the 90s. Again, we started in Australia after the Marysville fires of the early 90s, and we're working with them ever since. Later on, the USA, and now obviously Canada as well. We don't yet have statistics how many wildfires were not started as a result of covered conductor being used. I'd have to talk to a statistician about that one. We don't know how to figure that out, even though we have people telling us what the effectiveness of that. I guess they need numbers, right? Again, we looked at what Southern California Edison said when they did their studies and the mitigation to cost ratio, that the covered conductor option is the most viable mitigation to cost ratio and the most effective spending of your dollars when you're working towards system hardening with respect to wildfire mitigation. SDG has not conducted studies to measure the effectiveness of covered conductor. However, number one, they estimated to be 70% effective. Again, the new estimate from SCE, not 60%, 70%. I would say it's a heck of a lot more effective than that, but we'll go with their numbers. Assuming it will be equally effective as bare conductor hardening at preventing equipment failures, and better than bare conductor hardening at preventing foreign objects in line contacts. Another thing that SDG&E said, which I found really important from an operations standpoint, again, we have all these things we're doing, monitoring and full change outs and cross arm change outs, and then we have PSPS, if it's dry and it's high winds, we're just going to shut the power off and throw the whole economy into standstill until the winds die down. But SDG&E said, in addition to its wildfire mitigation benefits, covered conductor has some PSPS benefits as well, raising the threshold for PSPS to higher wind speeds than bare conductor hardening. So that would be a massive benefit if I was a ratepayer or a consumer or just a person trying to run my home or my business and not have the lights go out every time it's dry and the wind picks up. Food for thought. Anyway, this is from SDG&E. So in summary, power lines are an inevitable source of risk for wildfire ignition. Mitigation tools and techniques are available both for bare wire, underground, and covered conductor systems. A covered conductor is a viable and cost-effective tool to combat this phenomena. And as we've seen recently with the news this year, last year, the year before, this problem is not going away anytime soon, unfortunately. So, yeah, we will be looking forward to your questions, and I will send you back over to our moderator. Thank you, John, and thank you, audience, for tuning in.
Yeah, thank you, Brian. Really interesting presentation. So as Brian mentioned, you can now ask your questions in the chat box that's part of the platform. So please do that. We do have a couple already. And we will take a look at those and send them over Brian's way. Okay, first one, Brian, that we have is, what is the typical delta between open wire construction and spacer cable?
What is the cost premium? Yeah, we used to say that at 15 kV it was about 15% more expensive than bare wire. 25 kV more, 35 kV, it might be 25-30% cost premium over bare wire construction. Probably now it's more like a 35-40%. If I looked at bare wire and I wanted to know what was the cost premium to build spacer cable, it would be, say, between 1.2 and 1.4 times that material cost. Installation cost would be about the same.
Here's another one. Go ahead, Brian.
Wild ballpark, say I've got a 25% premium for covered conductor system.
So here's one we have from, Maynard says, how are the risks quantified? We can identify risks as possible harms, but how much risk do these conditions represent? How are decisions made about whether or not we can continue with such measurable risks?
That's a very good question. I would say that that's above my pay grade. That sounds like something that would come from consulting firms that do risk analysis. Our desire here is to help designers at electric utilities and industrial sites mitigate risk by using design tools so that we will not create ignition. Or the cost of that risk or the cost of the ramifications is something that I am ill prepared to comment on.
The next one we have, Brian, is from John. John asks a two-part question here. Would you agree close proximity flame and heat age the covered conductor? Question is how much? And maybe you answered this question already, but what is the expected life of a covered conductor?
Yeah, okay. So would I anticipate that intense heat would accelerate the aging of a covered conductor? Yes, I would. I don't have any studies on that. No, we would look at, a covered conductor that was operated at maybe 90 C or 110 C, and we've done those studies, what happens to the material, but we don't have studies on what happens when you put a covered conductor in a chamber elevated to 1,500 or 2,000 degrees Fahrenheit. We do not have that information. It would also depend on how proximate, how close that heat was, and it would also depend on how long that heat was there. I mean, if I was doing an inspection after a wildfire and I saw a covered conductor and it was all black and crispy, I would probably want to replace that. So how much does intense heat accelerate aging? We don't know. We suspect it's not insignificant. We don't have a good answer on that, but certainly intense heat will accelerate aging, as John is hypothesizing. Second, what is the useful service life of this cable or of the high density polyethylene, whether it's XL or high density or low density or FR or high tech? We are allowed to say that you're good for the expected service life is good for 40 years. We know that if we say more than 40 years, we have to take, our legal department says we have to take out an insurance policy for failures after 40 years, something like this. Anyway, legal department says we can't say more than 40 years, so I've got to tell you 40 years. We have installations that were installed in 1951, 52, 1953, that have 72, 71, 70, whatever, 60 plus years of operation. Right at the edge of the sea, we've got saline stuff, contamination, all kinds of nonsense trying to kill it. After 72 years, 71 years, 70 years, those lives are still cooking away. They still look like $1 million, and they're still as alive as you can possibly want them to be. If you come to fly into Boston, I can personally take you to those installations for 51, 52, and 53 and show you them, have you get a look at them. So I can only tell you that that I'm legally allowed to say I've got a 40-year useful service life, but I know from a fact, from experience, that we've still got systems after 70, 71, 72 years in perfect condition.
Don't worry, Brian. When your legal department tried to register for this webinar, we flagged them and we blocked them. So you're safe. This is now Brian Traeger After Dark, and you can say whatever you want. This is the uncut edition. All right, next one comes from Mitt. I might have missed this one, he acknowledges, but is there a trade-off with ampacity? Ampacity decreases with covered conductor versus equivalent bare conductor?
Yes, absolutely. So at 15 kV, you have the same ampacity because that 150 mils of insulation on that jacket actually acts, instead of a heat sink, it acts like a heat radiator. That heat is radiated out into the environment. When we get to 25 kV and 35 kV, there's a crossover. I have so much insulation on that bare conductor that I have an ampacity derating, and that goes 15, 25, 35, 46, 69. When we get to 69 kV, I have fully derated that conductor ampacity by 5%. So yes, there is a trade-off, but it's minimal and it's negligible until you get to high voltages, 69 kV. Number one. Number two, when we go from bare wire, fully self-supported open wire construction, we usually use an ACSR or AAAC. When we're using spacer cable, we're always using AAC. I don't need strength. There's no tension in those phase conductors. It's not self-supported. AAC has a higher ampacity. It's easy to compact. It's less expensive. So yeah, by the time I get up to 69 kV, I've got 5% ampacity rating with a covered conductor. But 15, 25, and 35 kV is negligible, and there are even benefits using AAC. Next.
All right, I'm just trying to parse through these, Brian. We've got a lot of questions, so trying to get to them all. Here's one from Nat. It's another risk question, so feel free to answer it quickly. Given the state of litigation, does an electric utility need to eliminate risk completely to insulate itself from bankruptcy? Yeah, any thoughts there?
Yeah, the whole concept of completely eliminating risk is more of a philosophical topic. You will never, ever, no matter what you do, you're never going to eliminate risk. If you put the whole darn thing underground and covered it up with cement, you'd still have a 747 hit something and blame it on the utility. You will never eliminate 100% risk.
So this one's from Tamar. The question is, what is the time difference in terms of installation between bare and covered wire?
Yeah. Good question. We have utilities here in New England and one that we surveyed in Michigan that said they were installing spacer cable faster than bare wire. If you say, well, we're in a utility, we've never done it, our crews don't know anything about it, we have a service crew that goes out and supervises your line crew or your contractor. So I'm basically going to say there's no time difference between bare wire and spacer cable. And there's been surveys done, Edison EEI Institute and all kinds of stuff that says there's really no time difference between spacer cable and bare wire. And we can have our people on site to make sure that that's the case.
This one's from Keith. What voltage do you get from the surface of a 15 kV covered wire to ground?
Excellent question. If my voltage on the inside of the cable is 7.2 kV, which would be whatever, 13.2 to ground, the voltage on the outside of that jacket is pretty darn close to 7.2 kV. Okay, the outside of that jacket is fully energized. Is there a follow-up to that question?
I think that was it. The question was, what voltage do you get from the surface of a 15 kV covered wire to ground?
Yeah, you're going to get almost full voltage. You might get 99%, you might get 98%. And we have videos on YouTube where we're testing this with voltage testers and acoustic voltage testers. You get the full voltage. However, voltage doesn't kill. Current kills. Voltage doesn't start fires. Current starts fires. So, if you got a 15 kV cable lying on a wet tree and you're giving off 1/3 of a milliamp, you could probably be there for 10 years without ever having a problem. So again, full voltage. Voltage is not a problem. Current is the problem. We are controlling the current with the covered conductor. And again, I apologize to the audience here. We're answering questions rather quickly. Any question you have that's a hardcore question, you want photos of diagrams or drawings or IEEE papers or white papers or lab reports or type test reports or what they did in Europe or South, send me an email and I will endeavor to answer your questions in writing professionally with stuff that you can bring to your team and have an intelligent conversation.
Next one, Brian, is from Alex. If a wildfire does damage to a covered conductor, is there a way to repair or dress the damaged sections short of replacing them?
Well, probably not. I mean, if I was doing an inspection and I had a section of line that was all burned up, I would probably cut it out and splice in some new conductor.
This next one's from Jordan. How do you mitigate the risk from exposed energized connections with jumpers, taps, transformers, etc. if a tree tears the whole line down, breaking poles, and the line is energized on the ground? Both ignition risk and public safety risk when there is no fault generated and possibly no knowledge of conductor down.
Yeah, good question. This is a very good question, and it was addressed significantly by Southern California Edison and some of the folks in California. They cover everything up. So they cover the taps, the splices, the jumpers. They cover absolutely everything. Individuals submitting the question is a good question. I mean, So how about if I get a massive tree, it hits the pole, knocks everything off the ground, maybe even knocks the covers off of those live connections. Then you have exposure. Yeah, you have exposure. I mean, I guess if you don't want to have that, don't have any connections or jumpers or taps that are bare anywhere.
Next one, Brian. Diana points out that with climate change, lightning strikes have increased significantly. She asks if you happen to know in the U.S. West what portion of fires are being started by lightning versus power line problems.
Yeah, good question. In North American Western region, we have the lowest isochronic level in the whole United States. I mean, it's incredibly low, but we still have, every time I say this, somebody from LA sends me a photo of a lightning strike in downtown LA. Yes, yeah, California has lightning, but not a lot. How many wildfires have been caused by lightning? Now with the really hip and modern monitoring we have all these cameras on mountaintops. We're getting a better idea. We're getting more empirical data on how many wildfires are caused by lightning. And these would be in the statistics published by the individual utilities. Still pretty low, but not an insignificant number. However, lightning is not a cause of failure for spacer cable systems because of the massively high BIL. They are very system hardened to lightning.
All right, Brian, we got time for a couple of more here. Go on. You got another.
Many thoughts. Next question. Sorry.
I'll just let you run. You go as long as you want. We don't have to cap this thing off. This one comes from Troy at Austin Energy. He asks, how much does the added weight of covered conductors affect distribution design, such as pole loading, span lengths, and so forth?
Brilliant. We got a designer asking that question.
Good job, Troy.
Yeah, sure. That added covering does add weight, for crying out loud. So yes, if we're reconductoring 336, 175 foot spans, 15 kV, 336, 175 foot spans. We've already got class 3 poles. It's probably going to be just quick change out the spacer cable. That additional weight is not going to bother you. If we've got, we're going 477, or we're making the spans a little bit longer, or maybe my poles are class 3 or class 4 or class 5. What we're going to do is either you can do it or we'll do it. We'll do a PLS CAD simulation with your NESC, light, medium, heavy, your winds, it's ice and all that good stuff, and we'll tell you those poles are adequate. No, those poles need to be changed out. And we do these studies for utilities, and we do that free of charge. And we'll work with your engineering department to decide if you, on this line, if you're going to reconductor the spacer cable, if those poles are okay or you need pole change outs. But yes, your point is well made. There is additional weight, and in marginal cases, they need to be with PLS CAD or whatever modeling design software you're using. And we can do that for you or with you. Next.
Another one from Nat asking, are covered and FR cables resistant to UV degradation?
Okay, absolutely, positive. How we fix high density polyethylene or any other polyethylene for UV inhibition is we add UV inhibitors. It's chemicals that we put into the raw material, mix it up, heat it up, mix it up, and then we get UV inhibition. When we use FR flame retardant, it's the same thing. We're adding additives. So it's more additives, it's more ingredients in the recipe, but it's still UV inhibited. And it's still UV inhibited, and we still have, every time we make a new batch, we run the type test to make sure that we're doing, for UV, ASTM G155 or G26 or whatever it is, ASTM D23 for tracking. We check all of the type tests. And when we add in the FR additives, we got to make darn sure that one additive doesn't counteract another additive. But yes, they are UV inhibited.
And that's about all the time we have left here for Q&A. Do you have any last thoughts before I wrap us up?
No, just that I'm glad that we have so many participants. I'm glad that people are looking in for solutions. I'm heartened by the fact that we have so many intelligent questions, that people have been thinking about this and maybe considering it. And again, thank you so much for your time. Any questions you have, send to me personally. I am your private consultant. Thank you, John, and thank you, audience.
Yeah, a robust Q&A today, so that was great to see. And not often in webinars, Brian, do we see the audience keep growing and growing. Usually you expect a fall off, but halfway through you were really picking up steam and people must have really gravitated towards it. So happy to see that. Thank you all for attending today's webinar. If you missed any piece of Brian's presentation, you will soon receive a link after we conclude to watch on demand. And check out those documents. You've got a few seconds left here before we close out the platform, and you can click those. You'll still be able to access afterwards in the platform here. And make sure to fill out our survey on the challenges discussed in this presentation. Thank you all again. Thank you, Brian, and have a great day.
Thanks.